Hi, my name is Rodrigo Cedillo, and today I'm going to present my argumentative exam of the subject of process modeling using linear algebra. Okay, so basically in our argumentative exam, our role in a semiconductor company is to design a quantum well of electronic device. Our job is to use linear algebra and numerical method to solve the Schrödinger equation in a quantum well in order to provide electron confinement energies needed by the other teams to design the correct structure. In the instructions, said that the fabrication team had requested our calculations for a device that should emit light at a specific wavelength or color, and here we have the approximate values for our visible colors. Okay, so we see that our goal is to design a quasi-quantum well that emits red light at 650 nanometers. So for this argumentative exam, I made a little presentation that consists in 6 points. The first is we're gonna see the scenario and the objective. Then we're gonna do the physics parts, the ties and boundary conditions. Then the discretization and matrix engine problem. Then we're gonna go to the MATLAB implementation and the width search. Then we're gonna go to the results of our MATLAB code, plots and discussion, and we're gonna end with our conclusions. Okay, so as we see, our scenario and role in this numerical model team, well, basically the goal is to choose well width, and so the mission is at lambda 115 nanometers and in red light. Use effective mass approximation and an infinity square well model. Provide the EE1 electron and EHH1, that is heavy hole, confinement energies, and connect numerical results to device and design choices. So now we're gonna pass to the physics part. We're gonna see the time-independent Schrödinger equation that for an infinite square well 0xa, the independent Schrödinger equation will be this one, that equals to E, and with our boundary conditions that are these ones, and all this equals to 0. And our target photon energy is, well, will be that E lambda equal to this, and our design equation that will be this. Okay, so following our goal of creating a gas quantum well, we go to the next slide, that is central finite differences. That here I discretize the interval with nodes x equal to IH, and in where h equal to this one, and for interior nodes, the second derivative becomes a central difference, that is this one, and the matrix engine problem that turns the differential equation into a tridiagonal system. Okay, for the next slide, we have the matrix engine value problem and target. For this, I will turn back. So this yields the matrix equation of the Schrödinger equation of h equals to this with h equals to that, and our coordinates. So we have to compute the smallest engine value to get EE1. For design, I use EHH1 equals to 0.15 EE1. So the target is EE1 equals to E lambda minus EG, all that divided by 1.15, and that equals to this one. And for our next slide, we have our analytical first guess and infinite well. As we check, the infinite well formula gives EE1 equals to this one. And solving for EE1, we obtain our result of that, and that equals to 0.067 moments, and gives an initial estimate around of 3.65 nanometers. And I use this as a starting point for a numerical search. So basically the next step will be do our MATLAB code to prove this. Okay, with our MATLAB code we are searching three different things. We're searching A, we're searching EE1, and we're searching the mission. And obviously we have to see the two different plots. Before we pass to the MATLAB code, I just realized that my presentation look embarrassed, so I will do a fast recap of all that I said. Okay, so here we have our scenario and role that basically is what we have to do. I choose the red one, that is lambda equals to 650 nanometers. And this one is a time-independent Schrodinger equation that basically this describes the standing waves allow electron states in the well. Also, here we have the Meson energy in a quantum well design equation and the Meson target. Here we have the central finite different discretization that numerically solving the Schrodinger equation and give us the quantized energy levels. Also, here we have the slide of the matrix engine value problem target, that each step validates whether the design will produce the intended photon energy. And in this formula, this one, this gives the world width that corresponds to the desired emission wavelength. And finally, here we have our analytical first guess in infinite well, and this is our A, that is 3.65 nanometers. And with all this, we can pass to our MATLAB code now. So here is our MATLAB code. We run it to see that it works. So there it works. We have there our results, but first we're gonna go step by step in our code to see how it works. So first I put my lambda value, that remembering that I choose red color, so my lambda value is 650. Then the gas band gap at room temperature, that is 1.424 electrovolts. Then the electron effective mass in gas in 6.7% of free electron mass. And finally my N, that I'll use 400 intergrid points for accuracy in the finite difference mesh.